This video would teach you almost everything you would ever want to know about the number type in JavaScript. We will start off with an overview, but if you really want to understand how numbers work in the language, make sure to watch the video until the end. And please subscribe to our channel if you want to get more videos like this. Let us now discuss the number data type in JavaScript. Apart from regular numbers that we are used to, the number data type does include additional types such as positive or negative infinity, or even something called not a number. Now, if we will start off with a line of code where we place the number 40 inside of a variable, let num1 equal to 40. 40 in this case would be a value, and this value would be of the number type. Considering that this is source code, we can also refer to the 40 as a numeric literal. If we want to dig just a little bit deeper and try to understand a bit better what happens when we enter a value 40 and assign it to a variable, what would happen is that there would be an address in memory, and then 8 bytes of data would be allocated so that we can save this number. Now, 8 bytes of data means that to save the number 40 in binary, we would be allocating 64 bits of data. Now, we can define integers such as 40 using the number type in JavaScript, but we can also define fractions. So for example, if we have the number 3.14, the number 3.14 would again go in 8 bytes of memory, which would consist of 64 bits of data. And once again, we would have something that looks very similar to what we did with the integer 40. So notice that we are storing both integers and fractions in exactly the same way in JavaScript, in the same data type. So if we want to summarize the key characteristics of the number type in JavaScript, we can say that it is stored in 8 bytes in memory. Its type is double precision 64-bit format, which is used in a number of languages for their double type. JavaScript did not invent its own standard. In fact, it uses something called the IEEE 754 standard, which again is used in quite a few languages for the double type. And the same type of number is used, for example, in Java or C# in addition to other numeric types. So what is interesting in JavaScript is that we are mostly using one data type to describe everything. And we are using this data type to describe both integers and fractional values. It is very important for us to get a very good feeling for what exactly gets stored once we input a number. If we add a third line of code, const num3 equals to 3.14, the number here represents the first 100 digits from the number pi. And then if we would call back num3 and show us the value that was stored, we would see a much smaller number. So what is going on here? Well, it turns out that there is a way in JavaScript to in fact force JavaScript to give us more digits. We can use the number built-in object, which has a method which is called toPrecision, where we can tell JavaScript how many digits we want shown. So in this case, we tell JavaScript, okay, show us 100 digits. This is how many digits we in fact put in our initial number. We do that, and then we see that the numbers have changed. We have the numbers right at the beginning, which are shown in yellow, which correspond to what was initially input. And these were in fact the numbers that JavaScript gave back to us without defining the precision. We then have the numbers in blue, which are apparently different from what we just put in. And then we end up with a whole lot of numbers in green, which are all zeros. So what is going on here? Make sure to see the continuation of the video, which would be going over all of these details so that you'll get a better feeling for what's going on. But the main thing to be aware of for now is that JavaScript would often assign numbers, store numbers as approximations of what we put in. And this is especially true if we put in very big numbers or numbers with a lot of digits. We can summarize numbers in JavaScript in the following way. We can talk about finite numbers, which are typically the numbers you think of when you think of numbers. Right in the middle of them, you would have 0. Now, a caveat here is that you can have both a positive 0 and a negative 0. This is something that the standard that JavaScript uses allows. Outside of this range, we would have positive infinity and negative infinity. Now it's important for us to understand that infinity here is not mathematical infinity. All it refers to is numbers that are bigger than the acceptable range of the number values as defined by the bytes that we allocate in memory for a number to be stored. And the limits of those things are quite specific. For example, if we use one of the built-in objects in JavaScript, the math object, and use its power methods, its pow method, what we can do is we can figure out what is the value of 2 to the power of 1023, and we get a very large number. But if we were to find out what is the value of 2 to the power of 1024, we hit infinity. So notice there is a sharp boundary here. Another data type, which is probably the most confusing one in JavaScript, is the not a number one. And to find out more about this, again, make sure you watch the video until the end, because we will be covering all of those topics in a fair bit of detail. As with many things JavaScript, to really understand numbers, you have to peek under the hood. You have to understand what is happening in the background, how are numbers in fact stored. Now, a key thing to keep in mind is that for us to store a numeric value, we only have 8 bytes available to us, which means 64 bits. So if you think about 8 bytes as 8 boxes, and then each byte containing 8 internal bits to it, 8 additional boxes, altogether we would have a total of 64 bits available to us. And in these 64 bits, what we need done is to store both integers or fractions, very large numbers and very small numbers. This is actually quite a tricky thing to do, and the solution here is quite elegant, as you will find out. So for us to handle all of this, we in fact separate the series of 64 bits into 3 components. We have one bit which represents the sign, whether something is positive or negative. We then have 11 bits which represent an exponent. All of this would make a lot of sense in just a little bit. And then we have something called the significand, which is also known as a mantissa or a coefficient, which is where we will be storing most of the digits that would represent the number. So if we think about base 2, and again remember that all of these numbers are stored in binary, base 2 would be raised to a given exponent, which will be defined in the 11 bits corresponding to the exponent. And then this whole number will be multiplied by the significand, which is a normalized binary number where we would have most of the digits which are involved. And in addition to that, all of this would be multiplied by the sign. So if the number is negative, the sign there would indicate a negative number. This is very similar to scientific notation of decimal numbers. So for example, if we have a number such as minus 3.455554 times 10 to the power of 15, this is scientific notation. We will be doing something very similar, but for binary data. Let us now look at the components in a bit more detail, starting off with the sign. So if we have 0 for the sign bit, it means that the number would be positive. And if we have 1 for the sign bit, it means that the number would be negative. Things are as simple as that. Jumping to the exponent. Now, as we've already mentioned, the exponent has 11 bits available in it. And as you may remember, an 11-bit exponent basically means that we would be raising 2 to different powers, starting from 2 to the power of 0 to 2 to the power of 10. How many numbers can we play with here? Well, if we put in ones for all these bits, the biggest possible number would be 2047. So this is the possible range. So in a very simple world, we could have just raised 2 to the power of 2047, but this is not what in fact happens. There are a few complications here. First of all, if we add all ones, this is actually the number that is reserved for the number infinity. So we cannot use it. So in fact, we have one less number to play with. So the maximum here would be 1046. Notice that there is a 0 for the very first bit in this series. And the other main thing that we want to do is we want to be able to use this field to describe both very large and very small numbers. And we are about to do a very neat trick here. What if we move the 0 to the middle of this range, to the value of 1023, which would then give us the possibility to describe both positive and negative numbers using the same 11 bits of data. So the maximum number would be 1023, and then the smallest possible number would be minus 1023. 1023 would correspond to 2046, and negative 1023 would correspond to 0. So notice that we've done a very neat trick here. So in fact, we can, by the same 11 bits of data, we can describe a number as big as 2 to the power of 1023, or as small as 2 to the power of minus 1023. Remember, having a minus in the exponent means a lot of zeros after the decimal, so a very small number. Now, we have already talked about how there is a limit between finite numbers and infinity. Well, this thing is real. So for example, if we would raise 2 to the power of 1023, we would get a very large number. We have seen that before. And if we raise 2 to the power of 1024, we get infinity. So any numbers bigger than that would give us infinity. Notice this is the hard limit, and the reason why it is there is because we have 11 bits available to us for the exponent part of the number. So what about the significand? Well, what the significand represents is a normalized binary number. That means a binary number which is in the format of 1 point something, zeros and ones. Now, to understand normalized numbers, let us start off with a decimal example. So if we have the number 111, you can think of it as having a decimal point immediately after it. So it is like having 111 and then a decimal point. So for us to go to this scientific notation, to a normalized number, what we need to do is we need to move the decimal point a couple of spots to the left, which means that we are also multiplying the number by 100 or to 10 to the power of 2. So this is how scientific numbers work. Well, we will do exactly the same thing with 111 as a binary number. So remember, to have 111 as a binary, we would represent the number by a series of ones and zeros. And it turns out that the series of numbers that adds up to 111 is 1101111. So this is a number. Again, we can imagine that there is a decimal point immediately after it. So how can we normalize the number? Well, we have to move the decimal point to the left, actually 6 times. So the normalized version of 111 in binary would be 1.101111, which is raised to 2 to the power of 6. So if we want to represent the entire number, we would have, this is a positive number, so the sign would be 0. The significand would be 1.101111, and then we would multiply the entire thing to 2 to the power of 6. Now we have to represent the 6 also in terms of binary. But remember what we need to do. We would not just convert 6 to binary, but we would first add 1023 to it, because we are dealing with this biased exponent. So for us to get 6 plus 1023 is 1029, and the numbers that represent 1029 are shown in red below. So if you look on the top left, the ones that we need to put in the exponent are the following. So we need to put 1 right on the left of the exponent and then 2 more ones towards the right hand side. So this is the exponent that is needed. What about the normalized portion of the significand? Well, we will do another little trick here, because all binary normalized numbers would start with 1 point something. It turns out that we don't in fact need to save the 1 point in our binary number, because we are trying to preserve as many bits as possible. So you can think of having 1 point in the gap between the exponent portion of the number and the significant portion of the number. So the numbers that we would actually record would be the bits after the decimal points, which in this case would be 1, followed by a 0, and then 4 ones. Now that we understand how numbers are stored in memory in JavaScript, we are ready to understand what the different types of numbers that are allowed are. For example, if we have the number 0, all a 0 is a number which has all 0 bits in the 11 bits of the exponent and all 0 bits in the 52 bits of the significand. Notice that there is no condition for the very first bit, and we do in fact allow a positive 0 and a negative 0 because of that. This might sound strange, but again, the designers of this system have decided that this is a useful thing to have in a language. So for example, if we would run the following code, 1 divided by -10, the answer is -0. On the other hand, if we compare positive 0 to a negative 0, the answer is true. Now this is not true for any other number, so -1 is not equal to 1, but the designers of the language in the ECMAScript specification, which is the specification of the language that browsers, etc. are using, it is clearly stated that if we compare two numbers, x and y, and if x is positive 0 and y is negative 0, the comparison should return true. If x is negative 0 and y is positive 0, again the comparison should return true. How do we deal with infinity? Well, to define infinity, we would add all ones in the 11 bits of the exponent and all zeros in the 52 bits of the significand. So this is the definition of infinity. Notice that the first bit is again free, so we can have positive infinity and negative infinity as we have discussed elsewhere. What is infinity? Well, anything greater than 2 to the power of 1023 would give us this number. And let us view a few examples. So if we have infinity and if we multiply it by a number, by a finite number, we would get infinity. If this number is negative, we would get negative infinity. If we take a number and if we define it by infinity, for example, dividing -10 by infinity, we actually get 0. But notice that the 0 here is a negative again. Now, again, we have to remember that infinity in JavaScript is not mathematical infinity. All it means is a big number, a number bigger than we can handle by the bits and bytes available in memory. So this is why it sort of makes sense that we start approaching 0. If we have -10 divided by 0, and this is a strange one, in mathematics we are not allowed to divide anything by 0, but again, because in JavaScript very often the numbers are approximations, the designers of the language have decided that the most reasonable thing for us to do is in fact to have this equal infinity. So if we have -10 divided by 0, this would give us -infinity. And again, those are a few things which we just have to be aware of and we have to know. And these things are in fact described again in this ECMAScript specification of the language, where it is clearly said that division of an infinity by a 0 results in an infinity, division of an infinity by a non-zero finite value results in a signed infinity, division of a finite value by an infinity results in 0. So all of those things are actually given to us as rules that browsers have to follow. And in this case, we have another condition. Division of an infinity by infinity results in nan, not a number. So let us say a few words about this non-a-number type of number, which is probably the most confusing one of the bunch. We have already discussed finite numbers, 0 and its positive and negative variety, positive and negative infinity, but there is one last type of number that usually people find the most confusing, which is the nan, the not a number type. Now you can think of the not a number type as a hack, and we tend to use it when we've done something wrong or we've done something illegal, for example dividing 0 by 0. Using none allows us to get this unexpected value but yet not stop the program from running and debug the problem later. So how do we define a not a number? We can have 0 or 1 for the sign, so both positive and negative would be allowed there. We would have all ones in the 11 bits of the exponent, just like the infinity numbers. But unlike the infinity numbers, which had all zeros in the significand, this time around we would have any number but all zeros. So even if we have a single one, the combination of bits on the screen would give us the not a number type. So let us view a few examples of not a number. For example, dividing 0 by 0 gives us not a number. Multiplying anything to a not a number gives us not a number. Adding, subtracting would lead back to the result of not a number. And even taking this to an extreme, not a number is in fact not equal to itself. Again, this is something that people find very strange. But again, if you think about debugging and think about the fact that not a number is something which is a value that we need to look at afterwards, this sort of makes sense. So not a number with triple equal, not a number. Strict equality gives us false. So this number is not equal to itself. We are now ready to understand safe integers. What do we mean by safe integers? Well, the number object in JavaScript has a property called maxSafeInteger. So if we run that, we get a decimal number. So it turns out that this is the biggest number that we can safely use in JavaScript. If we are interested in integers, i.e. whole numbers, anything bigger than that would result in some kind of rounding. Now, instead of having this memorized, let us understand what happens. This same number in terms of binary and in terms of binary exponent would give us the ones that we are currently seeing on the top left. Now these are the numbers that are resulting in these ones, which gives us the number 1075. Now if we subtract 1023 from 1075, we get 52. So this is actually the number represented in the exponent, which means that the exponent here is 2 to the power of 52. So notice the maximum integer number has nothing to do with us running out of exponent space. We can have a lot more exponents than 52. So if we do the rest of the number in bits, we would see what the problem is. Notice all ones. So in fact, the maximum integer number is the place where we run out of significant bits, right? So this is the biggest possible number we can include in a significand. Let us view a few examples. For example, if we take the maximum safe integer, the number which is seen above, and then if we add 1 to it, what we get seems to be reasonable. So the first number ended with 91, the second one ends with 92. That is fine. But notice what happens if we add 2 to that number. So we take the same number which ends in 91, we add 2 to it, and notice we again end something that ends with 92. Something has gone wrong. Notice we are already rounding. We've run out of numbers. And if you want to do even something more interesting and to compare the maximum safe number plus 1 to the maximum safe number plus 2, you actually get that the two numbers are equal. So we are taking the same number, we are adding 1 to it, and then we are adding 2 to it, and we are comparing the results, and we are getting that their two results are equal. And again, the reason for that is because we've gone into this unsafe territory where we've started rounding things. What happens if we take the maximum safe integer and add 4 to it? Again, the initial number ends with 91. If you add 4 to 91, you expect 95, but we in fact get 96. So notice what happens here. We've run out of space and we start rounding things. So these are things that we do have to be aware of. Something else which many people get confused are why simple decimal numbers give us strange results in JavaScript. And the reason for this is because sometimes simple decimal numbers do not make simple binary numbers. For example, if we have the number 1 which we can represent in binary as 1 times 2 to the power of 0. This is how we would describe this number using the bits notation. Notice this is quite straightforward. We just have a number of ones in the exponent and then everything else is 0. If we have 0.5, which is 1 divided by 2, in binary this would be 1 times 2 to the negative 1. We again have something straightforward where we have only ones in the exponent and then 0 in the significand. If we divide this number by 2 and end up getting 0.25 in decimal, in binary this would be equal to 1 times 2 to the power of negative 2. We again have a simple number to deal with. If we divide this number by 2 in turn, we would again get a simple number to deal with. So notice that binary numbers work very well as long as we are multiplying by 2 and dividing by 2. This is why they are binary. But what would happen if we have a simple decimal number, for example 0.3? How would 0.3 be represented in binary? The exponent would be straightforward. It would be the same exponent, in fact, 2 to the power of minus 2 as we had for 0.25. But notice what happens in the significand. We keep getting 2 zeros, 2 ones, 2 zeros, 2 ones. This is, in fact, a number which does not end. So if we need to represent this number in binary, we would run out of significand again. So we would be rounding things off. And the moment when we start rounding things off, we start getting strange numbers. So 0.3 would not be equal to 0.3, it would be an approximation of that number. So if we would run a line of code, for example, let num3 equal to 0.3, a decimal number, and then if we do the two-precision game again, so that we give the result now with precision of 53 digits, this is what we get. So notice, the real number that got converted to binary and then back to decimal is not 0.3 anymore, but it's 0.29 and then a whole lot of digits afterwards. And this is why one of the textbook's examples of why JavaScript is weird, which is why 0.1 plus 0.2 equals to 0.3, this gives false. Well, this sort of makes sense now. All of these numbers are approximations. They're not these nice numbers that work very well in binary. And because of that, if we add two of these and then compare them to a third one, they don't add up perfectly. You can imagine the number 0.299, etc. is not really equal to 0.3. So if we add a few of these numbers together, we would not end up getting exactly the same result.